Okay, so this is I guess a book or a class or something on machine learning. And we can see that it has mathematical tools, probability and statistics. Then it goes into machine learning, dimensionality reduction, regression, classification, clustering, and so on. Well, we want to start with chapter 1 and chapter 2. That's what we're going to use from this site. Now we can see that chapter 1 is called Mathematical Tools, and it does a recap of linear algebra. Univariate functions means functions of just one variable, which is not really very interesting for us, but it's good as a basic analysis of functions. Then we'd want to go on to multivariate functions and the chain rule, and then matrix calculus, and what are called computational graphs, which are just sort of a way to think about the chain rule, and a little bit of what's called information theory. And then we have probability and statistics, which will also be important for us. So we need to know these concepts. Especially we need to know about conditional probability, independent events, random variables, and calculations with random variables, and random vectors. So some of this you've done before, but let's just see how they explain it and check about their notation as well. So here we have a vector, and they're writing it vertically, which is pretty common. And we can see that there are n elements in this vector, and we can see that the notation that they're using is a bold lowercase x for that. And since there are n elements, we say that this is a vector in Rn because the elements in here are real numbers, right? We're putting numbers in here, right? That's typically what we're doing in data science, machine learning. And so we say that those are they're in R. Each of them is a number, and there are n of them, so it's Rn. Now the format here is a little strange because here they're talking about something else next to this, but we'll check this as well. But let's go through, not look at this yet, and just scroll down through this. So one important point that they make is that we can think of vectors as points in space. In other words, an ordered pair like this, for this would be in R2, or we can also think of them as arrows. Now, just like with regular numbers, we talk about adding two vectors, but it's not the same because vectors are not just regular numbers, but we still have an operation called addition, which we use with vectors, and here they explain how to do it, and they say that when you add two vectors, you'll get a new vector, but they don't tell us yet how to add them, but we know that you just add them element-wise or element by element. So in other words, z1 is equal to this one plus this one, and zn is equal to this one plus this one. And then we can also talk about how to add vectors when we're thinking of them as arrows, and we know that you can, here they use the word concatenate them. Like you draw one, and then you put you take the tip of the, you take the base of the next one and put it at the tip of the first one. So you go here, and then you get another one that might go up here. Okay, then we also have scalar multiplication, and we can also we can multiply a vector by -1, and because that's a scalar, and we do this and we do that. So that's related to scalar multiplication. And now that we have that, we can talk about subtraction as just x plus negative y. Then they also mention we have the zero vector, which means has this property, and of course the zero vector has zeros in all its entries. Okay, let's go back up to here and see what they're talking about here. This is just another concept, uh, certainly related to vectors, but it's called the concept is real vector space. So what is a real vector space? It's a set V of vectors. So it's a collection of vectors. So we might have, let's talk about vectors in R2. So we might take a bunch of vectors in R2. Maybe we take all of the vectors in R2, or maybe we just take some vectors in R2, and that would be our set of vectors. So we might only have 3 vectors, and that would be the set V. Or we might have all the vectors in R2, and that would be the V. So in any case, what is a real vector space? It's a set V of vectors, and we need to have, in addition to this set, they say we need 2 operations. So we have 2 operations already. We've already defined 2 operations. One was addition of vectors, or they call it vector addition. And the other one is we have scalar multiplication. So we have 2 operations. So we can say that we have what's called a real vector space. So as long as you have a collection of vectors and well, sorry, that's not quite true. But anyway, we have a collection of vectors and we have some operations, 2 operations, then we're on our way to having a vector space, actually. I forgot to say that there are certain properties that have to be satisfied in order for this to be called a vector space. So what are the properties? Okay, well, it looks like they left out one very important property, as far as I can see. But anyway, let's just go through these. So first is that you have associativity of the addition operation. So that just means that if you have this, you can also do it this way. So if you can do these 2 first, or you can do these 2 first, and it shouldn't matter. If it does matter, then you wouldn't call it a real vector space. Okay, you also have commutativity, which means you can switch the order. You also need to have an identity element, and in our case, the identity element is you talk about the identity element with respect to the operation. So with respect to the addition operation, so we already know what the addition operation is. We just talked about it over here. So what does the zero element mean, or the identity element? It means that when you take any x and you add it, because we're talking about addition, you get x back again. That's called the identity element, or in this case called the zero vector. Okay, and then you need to have inverses. And what does that mean? That means that when you add x, we're talking again about adding. So when you add the identity element to x, you get the zero vector. And that, of course, is just the negative of x. Gives you the zero vector, right? If you have x, let's just make up a vector x, and another and then take the negative of it. And you, of course, if you add those two, you will get this. So that's true about the system we've defined over here. So far, everything, all these properties are satisfied by this system we defined over here. So it sounds like this Rn is going to be a real vector space, but we have to check the rest of them. So this also has to be true. Now, these all only had to do with addition, right? All these properties. But this one also is a kind of combination. It's a property about that includes the addition and scalar multiplication. So it's called distributivity of scalar multiplication. So it says that A times, that's scalar times, scalar multiplication, x plus y has to be equal to this, and also we have this. So these both have to be true, and that will also be true for this particular system over here. And there's something called scalar and So I guess you can do this as well. And there also has to be an identity element for scalar multiplication. And in our system over here, that's just 1. Of course, 1 times x gives you x. So this is a kind of, this here is, we know what this means, Rn or R2 or R3 or whatever. But we say that all of those are examples of what we call a vector space, a real vector space. But we can also, actually they talk about what they call a real vector space. So this is a real vector space because these elements in here contain real numbers. But then they say without the word real, we can also just talk about vector space more generally. And they say that, for example, functions have that, satisfy all of these properties. So if you take, first of all, we have to know what we mean by addition. So here we know what we mean by addition. We mean adding. We know we know what we mean by addition here, but we have to know here if we're talking about the elements are not these kinds of things, but rather they're just functions. So this is like a tuple, right? But we're not talking about that now. We're not talking about tuples. We're going to give another example of what's called a real vector space. I'm sorry, of a vector space. So this is a real, what we would call a real vector space because the elements in here are real numbers. But we can just generalize this and say, well, let's think about functions. Okay, so instead of x and y being tuples like this, let's suppose x and y are functions. And of course you know what functions are, like x squared is a function, and x cubed is a function, or 3x squared plus 15 is a function, right? Of course we know what functions are. So, but do we know what we mean by adding two functions? Because we have to have an addition operation. Yeah, but we do know what we mean by adding functions. Like if you have x squared and you have x cubed and you want to add them, of course we know what to do. Just write down x squared plus x cubed, and we know what that means. So we do have addition for functions, and we can also multiply a function by a number. So we do have a multiplication operation called like of scalar multiplication, similar to what we did here. So actually that system that we just defined, the set of all functions, and we can of course add them. We can do scalar multiplication, and this addition is going to satisfy all of these properties. Like if you take one function plus another like that, or you can do the first two functions, add them first, and then do this one. It's not going to make any difference. And it doesn't matter if you put one function here and the other function here, or you reverse the order of adding them. It's not going to make any difference. And then we have to think about what's the zero element, or the identity element for the functions, for function addition. But that's just like the function which is set equal to 0. So set equals to the constant 0. So you can check that out. You can confirm that yourself, and you can check all these other properties, and they're all going to work. So we can say that instead of having these things, we can have functions as our elements of the set. Remember, we needed a set of items. We didn't say that the set has to look like, something in here. We just said it has to be a set of anything. That's all it says, really. But we have to have operations between those things. So it doesn't have to be elements in Rn. It just says a set. That's all. Okay, and we'll call the elements of that set vectors. So here, what is the set of things? It's functions. So that's our set. And then we need an addition, but we have a natural idea of addition for functions, so we may as well just use that as our addition. And we have multiplication by a scalar. So then we just have to check all the properties, and then we can say that forms a vector space. The set of all functions forms a vector space. Okay, Well, we don't really need that concept for machine learning, but they did put it in here, so we quickly reviewed. Okay, the next thing is basis vectors, and let's take an example. So they say, suppose we're talking about R2, so 2D, 2 dimensions, and here we have x is equal to this vector, but it's, we want it, they want to write vectors vertically, but here they wrote it horizontally. I guess they didn't want to take up a lot of space, so they have to write t there to say that they really mean the vertical version of this, because it's the transpose. So suppose we have that, and then they say suppose we draw it in the standard coordinate frame. So of course you know what that. So that means something like this. So we have 3, 2. So then they say, look at this vector, 1, 0, and look at this vector, 0, 1. And of course we know what that means. So here's 1, 0, and here's 0, 1. And those are called basis vectors. And in physics we call them I and J. But here they're going to call them E1 and E2. So we can call them I and J, or we can call them E1 and E2. And they have a special property, and that is if you have the original one, which was 3, 2, then you can form this, and this will give you this, of course. So let's just check that. Here's 1, 0, and here's 0, 1. This is 1, 0, that's here, and E2 is here. And we're writing them properly here because they're vertical. Here we had to do the transpose. So here we're writing them sort of properly, and we're writing the 3, 2 sort of properly. So we can say that 3, 2 is some multiple of E1 plus some multiple of E2. Now, if you take some other vectors, instead of this blue one and this blue one, let's say you took, let me just draw 2 other ones. Or let me just say, suppose we use this for one of them and the yellow one for the other, then I can still take a combination of these two to express 3, 2. So let's say, yeah, what should I make this? Let's say that was 1, 1. It's not, the length is not 1, and we like these basis vectors to be of length 1. This is 1, 0, so that's clearly of length 1, and this is 0, 1, so that's clearly of length 1. But let's just take this one. It's not of length 1, but we won't worry about that. So sorry, you can't really read this, but this is 1, 1, let's say. Okay, now let's say, so I'm taking this blue one and then 1, 1. So I'm still taking the blue one, 1, 0, but I'm taking 1, 1 here. So I can still write this as some constant times this one plus some constant times this one. You can do that because what you're saying is that if you take a multiple of this plus a multiple of this, you can get to this vector. And that's obviously true even if I use the blue one and the yellow one, right? I can go a certain amount in this direction and then a certain amount in the yellow direction and get to here. So it's just how much do I have to go in the blue direction and how much do I have to go in the yellow direction, and that tells me that how much I have to multiply this times plus how much I have to multiply this times to get here. So we can do that. We can get to here with a combination, a scalar multiple combination of this and this, but these 2 blue ones have a nice property. Of course, we can do it with the blue ones as well. We can go a certain amount in this direction plus a certain amount in this direction to get to the green. But the blue ones have a kind of nicer property, and that is if we want to know how far we should go, use the E1, and how far we should go using E2, it's just 3 and 2. It's just these numbers here. So that makes it really easy. I don't have to think about it, how to express 3, 2 as we call this a linear combination of these other two vectors. It's just 3 and 2. I have to multiply this by 3 and this by 2. Now, if we tried to do it with the blue and the yellow, it's not going to be so clean. We'd have to figure out how much in the blue direction and how much in the yellow direction to get to 3, 2. But if we use these ones, so these are kind of special in the sense that they're a lot easier to use to express this as a combination of these two. But that doesn't mean that we can't use the blue one and the yellow one. We can. So E1 and E2 are called basis vectors for this 2D space. And that just means that we can take a combination of them, this kind of combination, which is called a linear combination of them. That is, we can take the first one times something plus the second one times something else and get to here. So these two, E1 and E2, are called a set of basis vectors for 2 dimensions, or for R2. So right here they say, are E1 and E2 unique? No, we just argued that they're not unique. Are there other vectors, B1 and B2, that we can still express any vector, like for example 3, 2, as what we call a linear combination of them, of B1 and B2? No, yeah, we can do that for lots of B1s and pairs of B1s and B2s. In fact, as long as B1 and B2 are not in the same direction, we can do it. If B1 and B2 are in the same direction, it's not going to work. So if we use the green one as B1 and the orange one as B2, we can't get to, whoops, that's wrong, sorry. I didn't mean to use the green one. If we use the blue one and the orange one, they're both in the same direction, I can't get to the green one using a linear combination. I can't add these in any way to get to here, because when I add these, I'm always going to stay down here. So if they're parallel, it won't work. But as long as they're not parallel, for example, the blue and the yellow, we can express any vector, for example, the green vector, as a combination. That just means we can go a certain amount in one direction and then another amount in the other direction and get there. So they say here, let's try it with this B1 and this B2. Can I write 3, 2 as a combination of these two? So we're saying this, and can we find an x and a y? And it will work out. You can do it. That is, you can find an x and a y, which will give us a solution to this equation. We can call this an equation because there's an equal sign there. So this concept is about what we call basis vectors, and more generally, remember over here, I guess what they're doing is the more general scenario. So here, more generally, a vector space V is an n-dimensional vector space in case n linear independent vectors exist such that any element of V can uniquely be written as a linear combination of these basis vectors. So what they're defining here is what is the meaning of the n-dimensional part of it. In other words, when do we call something two-dimensional? When do we call something three-dimensional? For example, well, we certainly have a feeling for why we call this this kind of thing two-dimensional, but they're giving us a slightly different way of thinking about it, and they're saying something is two-dimensional if every element in the vector space can be expressed as a linear combination of just two vectors. So for example, of course, R2, everything in R2 can be expressed as a linear combination of 1, 0 and 0, 1. In other words, I and j. So there are two vectors in R2 from which we can express everything, every other vector, every vector in R2 as a linear combination of them. And by linear combination, they mean that you take the first one, so that might be I or this one, and you multiply it by any, you have scalar multiple, and this you take any constant, and you do that to the last one, which in this case was just one more, this one, which we call sometimes J, and that's what we mean by a linear combination of them. And if we take a linear combination of this I and j, we can express any vector in here. So that means we call R2 two-dimensional. But of course we would naturally call it two-dimensional. We don't need that definition. But this is another way of getting at the fact that it's two-dimensional. Now, that's not quite complete, what I said, because why don't we call it three-dimensional? Because I can take, of course, I could take three vectors, like I could take this one, and any other vector and add it on here, and certainly I can get 3, 2 as a linear combination of those three vectors, because I can do it just with these two, and then I could just use like plus 0 times the third one. So that would be a linear combination of the three vectors. So why don't I call it three-dimensional instead of two-dimensional? Why don't I call R2 three-dimensional instead of two-dimensional? Or why don't I call it four-dimensional? Because I could certainly take a linear combination of four vectors that include at least these two, and then two more over here, and write every vector as a linear combination of those four, because I can do it with just the two. So I could just use 0 times the next one and 0 times the next one. So it's not really clear that what we said isn't quite right. So again, here they seem to have made a mistake, actually, because obviously it's not true. Here they say a vector space V is an n-dimensional vector space in case n linearly independent vectors, I'm sorry, I didn't notice this word, in the independent vectors. So that's the key, that the vectors that we include, like this one and this one, have to be independent. Now, we didn't talk about what independent means yet, but sort of in one sense we could say that none of them are parallel to any others, but that's not quite the best definition. But that's a kind of way of thinking of it. But basically it means that these two vectors are linearly independent if we can't write this one as a linear combination of this one, or in this case, as a scalar multiple of this one. But if we want to talk about three vectors being linearly independent, we would say that, say, the first one cannot be written as a linear combination of the other vectors. That's what we mean by linearly independent set of vectors. So in that case, if I was saying that you could take this one and add on another one, and of course I could write any vector over here as a linear combination of those three, but those three are not linearly independent. So that's why we can't say that it's three-dimensional. So these two are linearly independent, so we can say that it's two-dimensional. Okay, we didn't go through that in complete clarity, but maybe that gave you the idea. And now they introduce another word. A set of vectors spans the space V, and so these span R2, but also I was talking about throwing in another vector here, or maybe even two more vectors here. They also would span R2. So spanning just means that you can write any vector as a linear combination of the vectors here. Okay, now once we have a basis for a vector space like this, gives us a basis for R2, but I also said that, say, the blue one and the yellow one also give us a basis for R2, because we can get to any vector in R2 as a linear combination of the blue and the yellow one. Once you have a pair of basis vectors or a set of basis vectors, so if you have the two blue ones or if you have the yellow one and the blue one, then you can express the green one as a linear combination, and the scalars that we multiply the blue one times and the yellow one times to get the green one, those scalars are called the coordinates with respect to that particular set of basis vectors. So of course, the coordinates with respect to these two blue ones are just 3 and 2. But with respect to the blue and the yellow one, it's not 3 and 2. We don't go 3 units in blue and then some number of units in yellow to get to the green. That doesn't work. So we have to figure out, well, how far do we have to go in the blue? And then how far do we have to go in the yellow to get to the green one? And those distances, the amount we have to go in the blue and the amount we have to go in the yellow, are called the coordinates with respect to this set of basis vectors. So here they use the word the coordinates. So for any n-dimensional real vector space, each vector v can be represented with n real numbers. So that's what we're going to mean the coordinates. Those are going to be real numbers with n real numbers, and we'll call those the coordinates. So they say, note that the coordinate representation of a vector, so we might say the coordinate representation is 3, 2, but that's when we are thinking of the basis vectors as 1, 0, and 0, 1. But if we had different basis vectors, then we wouldn't say 3, 2 anymore, are the coordinate vectors for, are the coordinates for the yellow vector. We'd have some other coordinates for the same yellow vector. So they say, carefully note that the coordinate representation of a vector depends on the basis that is implicitly used. Okay, the next section we will study is on what are called linear maps. And we'll see that in neural networks and deep learning, most of the operations turn out to be linear maps. And so that's the main reason why we will study this concept of linear mappings. Okay, let's talk about what are called linear mappings. So first of all, the word mapping just means basically just means function. So now they're talking about linear functions, but it's not really exactly what you think of when we think about linear functions of one variable. So it's a little bit different, but anyway, the word mapping means function, and now they're going to define what they mean by a linear function or a linear mapping. Okay, so a linear mapping is a mapping, we'll call it L. And so what does it do? It takes a vector from our n, so we're allowing inputs that are vectors. So that means it's multivariable function, right? Because we have a vector as the input, so there's many variables within that vector, many values in that variable. So we call it a multivariate function. Okay, so it takes a vector from Rn, and then it doesn't output just a single number. So we might have a function which takes many input variables, but just outputs a single number. But this is a little different. So it doesn't just output a single number, it outputs a vector. So that might sound confusing, but if you just think about it, you can do that. I mean, there's no reason why you can't do it. What's the purpose of it is a different question. But you can take a vector as an input, but also output a vector. It means output many things, not just a single number, but many different numbers at the same time as a vector. So that sounds confusing, but I think the confusing part is like, why would we want to do it? But if you just allow yourself to think about it, you can do it. Okay, but it's not just that. It's not just any such mapping or any such function, but it has to satisfy certain properties. And so there are two properties that it has to satisfy. So this mapping from Rn to Rm has to satisfy certain properties. So there are two properties here. So what are they? So you're going to take, if you take um, L of, now of course, if you take, so we said we can put in a vector in here, but it doesn't look like they're putting in a vector in here because X is a vector, presumably, and Y is another vector, presumably. So it looks like we're putting in two vectors, but not really, because before we um, put those into L, we sum them up. So of course, when you add two vectors, you get a new single vector. So that's what we're doing. We're putting that new single vector into here. But the thing is that we want to define what's meant by linear, and a linear mapping or a linear function will have this special property that if you take L of x plus L of x plus y, it turns out to be, it has to be the same as if you just took L of x and L of y. And by the way, they don't put the brackets here. I don't know, I guess it's just easier. Anyway, there should be brackets, L of x, L of y, but I guess it's kind of nice not to have to put them there. So they just don't put them there. But it really means L of x and L of y. So anyway, if you take L of x plus y, it's equal to L of x plus L of y. Okay, so this is what they just said. L of x plus y is supposed to be equal to this. Now these are supposed to be vectors, but I'm just going to take the simplest example, which is when we just have a single variable as the input, which we can think of as a vector as well. It's just a vector with just one element. But I'm just going to take these simple examples where we're just talking about putting a single element in. Okay, so we want to ask whether maybe this is linear, maybe this is linear, and maybe this is linear. Oh, I'm sorry, I didn't mean that. I meant that, whether that is linear. Now, commonly, we would probably say, oh yeah, this is a straight line, so that must be linear. Or we might say, this is not linear because it's not a straight line. Or we might say, this is linear because it's also a straight line. But that's not actually exactly what we mean by linear. So I don't know exactly why we're using the same word linear, or there's a way to think about it, but let's not worry about it. It's not exactly the same word as what we usually think of when we talk about a linear function, like this is linear and this is linear. So linear for us means this, that has to satisfy this property, and actually there was one more property, but we'll mention that one afterwards. But anyway, at least it has to satisfy this property to be linear. So for the first one, this is the question we want to answer. We want to know if we take L of x plus y, that is f of x plus y, which of course is equal to 2 times x plus y, is that equal to f of x plus f of y? Well, what is f of x plus f of y? It's 2x plus 2y. So is this equal to 2x plus 2y? And of course it is. 2x plus 2y, right? This is 2 times x plus y. Of course it's equal to 2x plus 2y. So in this case, f of x plus y is equal to f of x plus f of y. Okay, so therefore we could call this linear, at least this part of the definition. At least it satisfies this part of the definition of being linear. Okay, let's do it for this one. So, if we just thought about it as though it's asking us whether it's a straight line or not, we would say, yes, G is linear. But let's explore this condition for what we mean by linear. So here's the same question, but for G, is G of x plus y equal to G of x plus G of y? Well, let's see. G of x plus y is what? we take whatever is in here and we add 8 to it. So what do we get? X plus y equals 8. So should write that down here, but I'm not going to do it. But it's x plus y plus 8. Okay, that's on the left side. Now what happens if we do this? We get x plus 8. And what happens if we do this? We get y plus 8. So if we combine them, we get x plus y plus not 8 plus 16. So on this side we got x plus y plus 8, and on this side we get x plus y plus 8 plus 16. Those are obviously not equal. So this function does not satisfy this condition. It's not linear. And I'll let you work this one out yourself. This is also not linear. You can just try it. Do the same kind of thing that we just did here to see if h of x plus y is equal to h of x plus h of y. And it won't work. So h is also not linear. So anyway, this is one of the conditions for saying that something is a linear function, or actually a linear mapping. Okay, and then there's actually one more condition. It's not just this. It also has to satisfy this, and we'll look at this later. This is sort of simpler to think about, but we'll just look at it later. But it basically, let's just say this is the main condition. They're both necessary. Okay, but my examples were functions from R1 to R1, right? Like this takes a number as the input and gives me a number out as the output. So it's from R1 to R1, but we want to be much more general than that. Okay, so they're going to give us an example, and this example is going to be a mapping or a function from R2 to R2, so much more than sophisticated than our example was, but not totally sophisticated, because we want to be able to go from Rn to Rm. So the n and the m not necessarily the same, and here they're the same. But anyway, so what? Let's take a look at this one. So this is from R. They're going to give us an example from R2 to R2. Let's see what their example is. Remember that any vector in R2 can be written as like this. Remember, E1 and E2 are basically I and j, and they're just the basis vectors, right? So any vector in X can be written as a linear combination of the basis vectors. Okay, and I think that when we use E, we're referring not to just any basis vectors, but the so-called standard basis vectors, so like I and j. Okay, so X can be written like this. Now they're going to tell us, so L of X, if it's linear, then what? L of X, this means L of X, even though they don't write the brackets in there, is L of this, because we just said that X is this. So we can just put that in for X. But if it's linear, remember linear means that you can basically you can take the plus sign in here and take L of the first one, L of the second one, and put the plus sign out here. So that might remind you of something, by the way, like derivatives. If you remember about derivatives, remember the derivative of a sum is equal to the sum of the derivative. So we might say that we don't usually think of the derivative as a function, right? It's we might call it an operation. We don't usually call it a function. But if we did think of it as a function, it would be a linear function. We could think of it as a function, but we have to think about then what the inputs are. And let's not worry about it. But anyway, that should sound familiar to you. Remember, the derivative of a sum is equal to the sum of the derivatives. So that sounds like it's linear, and in some sense it is linear. Anyway, what we mean by linear, again, is that you take L of a sum, it's equal to the sum of L of the first plus L of the second. So here we're taking L of X, which we just said we could rewrite like this. And now, since it's linear, since we're saying it's linear, we're making the assumption that L is linear, then this can be written like this. Now, there's one piece that we didn't explain yet, and that is that you can, this property, the second property basically says that if you have alpha times x, you can pull the alpha out. That's the second property, that you're allowed to do this, or that something, if something is linear, it means that it satisfies not just this property, but also this property, which says that you can take the alpha outside of the linear mapping, or might say the linear operator, or the linear function. You can take the alpha outside of it. So that's what they did here. They took, because it's linear, we can write L of this one plus L of this one, but then also because it's linear, we can take the constant, the alpha, this alpha is a constant, we can take the constant outside, so we get the constant outside here, and then L of this, and then the constant outside, and then L of this. So that's if it's linear. Okay, so the next thing they point out is that this, remember that L takes vectors from R2 to another vector in R2. So L takes this, E1, which is a vector in R2, to a different vector in R2. And the same thing here. It takes this one, E2, which is in R2, to a different vector, but still in E2. So this thing, this thing, whoops, I can't do it, that thing, and this thing are both vectors in R2. Now, since this thing here is a vector in R2, remember that every vector in R2 can be expressed as a linear combination of the basis vectors. That is, any vector can be written as a linear combination of E1 and E2. Any vector. So in particular, this can be written as a linear combination of E1 and E2. So what does that mean? That means that this can be written as a combination of E1, here's the E1, and here's the E2, and this is just some constant, and this is just some other constant. They're just calling it, giving it a strange name, but it's just some constant and another constant. So this thing here, right here, can be written as a linear combination of E1 and E2. Now don't be confused, because this is not, L of E1 is not E1. So you might think, oh, of course it can be written as a linear combination of E1 and E2. It's just E1. No, that's not true. But it is a vector in R2, and so it can be written as some linear combination of E1 and E2. And these just are strange names for just some constants. They're just going to give them those names because it'll be useful in a minute. But anyway, they're just some constants. And we can do the same thing with L of E2. This thing. This is also a vector in R2, so it can also be written as a linear combination of E1 and E2. So L of E2 can be written as but we don't want to use the same constants as here because they're not going to be the same constants, so they just have different notation. Okay, so just to accept this notation, and all they're saying is it can be written as a linear combination of E1 and E2. So now they're going to replace this by this, and they're going to replace this by this. So they're going to get L of x, which is originally written like that, but then we're going to replace this part by this part, and then we're going to replace this part by this part. So we get this second line. But then, of course, we can collect the multipliers of E1. Here's an E1 and it has some multipliers. Here's another E1, it has some multipliers. We can collect those and say, put them all together here, multiply times E1, and collect the multipliers of E2 over here. So we can just rewrite all of this like this. So all we're saying is that we start out with, this is like our input, our x, and then we apply that linear mapping to it, which goes from R2 to R2. So it's going to take this to some new vector, which I put in light green over here. But remember that, of course, this is in R2, and so it has some coordinates with respect to these two basis vectors, right? We can write, you have to go out a certain amount in the E1 direction and a certain amount in the E2 direction. So those are the coordinates. We can write the coordinates up here, whatever they would be. So L of x is going to be the new light green vector, and it's going to have some coordinates. And let's call those coordinates x1 prime and x2 prime. So we might have called the coordinates of the darker green line x1, x2, but we're going to call the new coordinates something else. So we're going to call them x1 prime and x2 prime for this one. But these are the coordinates up here. This is the multiplier for E1, so that's the coordinates in the E1 direction, and the coordinates in the E2 direction are here. So the x1 coordinate is this, I'm sorry, the x1 prime coordinate is this, and the x2 prime coordinate is this. So we get this. x1 prime is equal to this one up here, and x2 prime is this one here. Okay, so we can do that. So what this says is we have this linear mapping, and this is all only true for a linear mapping. We started out up above, and we started out, I think, up here, and we said, oh, we can go from here to here to here if it's a linear mapping. So all of this is based on the fact that it's a linear mapping, which means it satisfies these two properties. So what we're saying is if we knew how this linear mapping works, that is, if we knew what these numbers are, then we could just plug them in, and for any given coordinates for our initial vector, we have coordinates for our initial vector, and that's x1 and x2, then we could just plug that in here. And if we knew L11 and L12 and L21 and L22, then we could figure out what the new coordinates are. And they're always going to be the same. I mean, the L11, the L12, the L21, and the L22 are always going to be the same. So once we know those, we sort of can figure out what the answer is going to be, what the new vector is going to be, just by plugging in the original coordinates, x1 and x2, x1 and x2, into this, and we'll get the new output, the new vector, the new mapped version of the original vector. And then they say it's customary to write these scalars, L11, L12, and so on, in a matrix. So L11, we could put it here. L12, we could put it here. L21, we could put it here. And now you can see why they use this notation, because this works perfectly with how we usually write the indices for the elements of a matrix. So that's why they use those particular symbols. So anyway, we can put them into this matrix, and we'll call this matrix L. Now, it's not a coincidence that we're calling it L when the linear operator was called L. But anyway, it's the matrix associated with our linear operator. But just because it's associated with it doesn't really mean anything. But actually, it turns out to mean a lot. It turns out to be very integrally related to the linear operator. And why is that? Because once we form this matrix, watch what happens. Suppose we start with this, we have this matrix, which we did all this crazy work to get it, but it's associated with our linear operator. But it's not just associated, it does exactly what we would hope it would do. What do we mean by that? Well, what we are saying is that when we put in x, um, into our linear operator, we're going to get something out, and if we sort of noted all these constants, we put them into this matrix, and it's not just arbitrarily put into a matrix, but what do we usually do with matrices? We multiply them times other matrices, or in this case, just times a vector. So in other words, if we take this matrix that we've just somehow devised, and we take our original vector, which we denote here like this, we get out exactly what we want. We can check that. If you take this times this, what do you get? You get this. And if you take this times this, what do you get? You get this. Let's check that again. If you take this times this, you get L11 times x1, L11 x1, L12 x2 right there. And then this one times this one, you get this and this. So it's perfect. When we take this matrix that we sort of dreamed up based on these coordinates, and or sorry, based on these entries here, or these constants, and we multiply it times our input, we get our output. So therefore, actually, it's not just out of laziness that they wrote Lx, right? I said it's kind of out of laziness. They didn't put in the brackets. But you could say that this is L times x instead of L of x. So that's kind of an amazing result. So we went through all of this. We started with a linear operator, and we found that there's a matrix associated with it. And where do these come from? Well, we have to find these, but these exist. We can get these. And once we get these, then we can just do matrix multiplication on the input vector to get the output vector. What matrix do we use? This matrix. In other words, to get the output vector, we take L times the input vector. So what we see is what we've seen from this whole discussion. We can sum it up in the following way. We can say if we have a linear operator, and we defined what we mean by linear operator here, and it's a little bit different than how we usually use the word linear, but this is the definition of it here. So if we have a so-called linear operator, and we saw earlier that not all operators, even ones that we would expect, functions from R1 to R1, we would expect them to be so-called linear. They're not always linear. They're not necessarily linear. So I gave you the example of x plus 8. And you would think that's linear, but it's actually not linear. But anyway, some operators are linear. Some mappings, I'm sorry if I've been using the word operator, but you can use operator or a mapping or a function or whatever you want to use. Anyway, some functions, some mappings are linear. And if they are linear, then it turns out that there's a matrix that's associated with that linear mapping, such that you can just multiply that matrix times your input to get the output. And there's the converse of that is also true. Every matrix multiplication is basically a linear mapping, because if we do a matrix multiplication, every matrix multiplication on a vector, if you do a matrix multiplication on a vector, you're going to get a new vector, and it has to be a square matrix, so that the input space and the output space have the same dimension. Like here, you have dimension 2 here, the input space, and you have dimension 2 here, the output space. So whenever that is the case, that operator will, if we think of that, I'm sorry, that mapping, if we think of it as a mapping, will be linear. So when you take a matrix times a vector, you're going to get a new vector. So you can think of that as a mapping, and it will turn out to be a linear mapping. Whenever it's a matrix, whenever you have matrix multiplication like this, it will be can be thought of as a linear mapping. And we also saw, just from this whole long argument, that if you have a linear mapping, it can be represented as matrix multiplication.